That's bright. Hey, everyone. Hey, let's take a look at the sample test. I thought I would do a few problems for you. The answers to the entire sample test, of course, are on Canvas. But, sometimes it's helpful to see, so I'll work them out step by step. So let's take a look. So I don't have time, unfortunately, to do the entire sample test, but let me just highlight a few things. Okay, so first of all, a lot of equations to be comfortable with, but you do not have to memorize them. All this equations and data in this table here on specific heat, heat of vaporization, heat of fusion, that'll all be given to you on the exam. Okay, so what do we got here? There's my pen. Cool. Well, osmolarity, that's kind of handy if you need to deal with osmosis. From a student point of view, first you should know what molarity is. That's moles per liter, and we already have it. So then the os refers to osmosis, and that's one of the colligative properties where you count up all the individual particles. So that's the clue. How many particles does this compound produce when it dissolves? Well, where's my periodic table? It's right here. So calcium chloride was the formula, right? So we got calcium right here, and we got chloride over there. Hey, and we're across the diagonal. We have a metal with a nonmetal, and that means ionic bonding. In which case, when you put it in the water, well, we probably should look at the solubility rules to make sure, but usually ionic compounds dissolve and the ions separate. Let go. Sorry, you can't see any of this, but I'm dealing with all the background options and stuff. And there we go. Okay, I think I got it situated. So that's the deal. Osmolarity means, hey, break up your compound to ions. And so there's 1 calcium and 2 chlorines for a total of 3 ions, 3 particles. And we multiply it times the molarity, 2.0 molar. And then that's 6.0 osmoles per liter. And we're done. Quick problem. Number 2, what will happen to a cell when it's placed in a hypertonic solution? So put yourself in the point of view of a cell. So you're inside the cell membrane, you got the nucleus and all, and then you got shoved into a solution, and it's all hyper out there. The kids have eaten too much sugar and they're bouncing around like crazy. There are too many ions out there, too many particles dissolve. Doesn't have to be ions, could be other things. And you have more water than the solution does, which means nature says, let's balance out the water. Water's going to leave the cell and you're going to shrivel and dry up, maybe die. Okay, so cell shrivels up, shrinks. What if it's isotonic? Iso sounds like isomer. Different molecules of the same chemical formula. Isotonic means you have the same number of particles, not necessarily the identity, same number of particles as the surrounding solution, so everything is fine. Cell maintains shape, doesn't change, everything's good. And then the third case, hypotonic. Okay, so I think of a hypodermic needle going under the skin, below the skin, which means if you're the cell and you're looking at the hypotonic solution you're swimming in, there are too few ions out there. There's a lot of water, more water out there than there is in you. So water is going to flow into the cell and expand. Cell expands, it could burst. There you go. I don't know if I'm going to go, I already said I'm not going to do the whole thing, but I am going in order here. Some of these are pretty quick. Let's knock these down. How come I can't scroll? I have to turn off the pen. No, I just got to get, oh yeah, it's over here. There you go. Okay, let's jump down to 4. Will a mixture of this compound and that compound be homogeneous or heterogeneous? So homogeneous means the same. Heterogeneous means different. So I always think of like Rocky Road ice cream is what my science teacher told me. Not necessarily chemistry, probably middle school, high school. If you go to different parts of Rocky Road ice cream, sometimes you get chocolate ice cream, sometimes you get a walnut, sometimes there's a marshmallow. It's not the same wherever you dig your spoon into it. Wherever the solution is, it could be different. Homogeneous, everything's identical throughout. And if you have two compounds here and you're asking the question, you want to know if they mix, or is it like oil sitting on water? Oil and water is heterogeneous, but if the molecules mix together, then it's homogeneous. So how do we know? The answer is like dissolves like. So if the compounds have similar intermolecular forces, IMF, intermolecular forces, then we predict if they're the same intermolecular forces, then they should dissolve in each other. So what we got here? Well, we got a bunch of C's and H's. Those are, well, C's and H's are nonmetals, but what kind of bond forms between carbon and hydrogen? That's what we had to memorize. It's completely nonpolar covalent. And then there's carbons connected to carbon here. When the same two elements connect together, it's nonpolar covalent. They're sharing the electrons fairly. But chlorine versus carbon, oh, the other thing you need to be aware of is that when you draw the molecules this way, you have to remember Hunk. 1, 2, 3, 4. Carbon prefers 4 bonds. Hydrogens and the halides prefer 1 bond. So if you're looking at the end of this molecule and you see that C, it's not C to H to H to chlorine. That's not how you interpret this because look, hydrogen would then have 2 bonds. It's only supposed to have 1. So that can't be right. Instead, carbon's making 4 bonds. So one of the bonds is to the rest of the molecule on the left, and then it has 3 more bonds. And that gives room for the 2 H's and a chlorine. Okay, so I'm asking, what's this bond? Well, they're different nonmetals. And chlorine is actually closer to fluorine. Instead of bouncing back and forth to the periodic table, why don't I just draw a mini periodic table right here? Yes. Argon, I think. Helium up here. Okay, here's the upper right part of the periodic table. And you can see that chlorine is right next to fluorine, carbon's farther away. And the trend is the closer an element is to fluorine, the more electronegative it is, which means in this bond, chlorine's not sharing fairly. These bonding electrons are being pulled towards the chlorine, starting to make it a little bit negative, and carbon is losing those electrons. It's becoming a little bit positive, and now we have plus and minuses forming. This is now a polar covalent bond. Okay, so this molecule is made up of a lot of nonpolar covalents, but there is one polar covalent bond in here. And so it turns out if a molecule is only nonpolar covalent, then the intermolecular force is London dispersion or van der Waals. If it has polar covalent bonds and they don't cancel out, and the molecule then is polar, so yes, it is a polar molecule. Polar molecules can do the stronger force, something stronger than intermolecular force. Yes, London dispersion forces, and that is dipole-dipole. Among the 3 intermolecular forces, hydrogen bonding, H bonding, is the strongest, but it requires that the molecule contain a nitrogen to hydrogen bond, oxygen to hydrogen, or a fluorine to hydrogen. And this one, remember, Hunk, halides, fluorine's a halide. It only makes 1 bond. So this is the only molecule that has an HF bond. It's hydrofluoric acid. So hydrogen bonding is going to come about mainly when you find a nitrogen. Hey, here's a nitrogen. Does it have a hydrogen? Or if you have an oxygen attached to a hydrogen? So that's the question. This nitrogen follows this carbon. Okay, so this carbon makes 4 bonds, right? 4 bonds. 2 of them are to H's. And then there's a nitrogen. How many bonds does nitrogen make? Honk, it makes 3 normally. So give it 3 bonds. It'll then have a lone pair, so it can have an octet of electrons. And now, in parentheses, a CH3 group. CH3, remember the hydrogen bonds once, carbon bonds 4 times. This is a CH3 group, and there's 2 of them. The only way you can get 2 of these groups attached here is connect the carbon next. And look, nitrogen is attached to 3 carbons, not a hydrogen. This molecule cannot hydrogen bond, but the carbon, the nitrogen connection, those are different nonmetals. Nitrogen's close to the fluorine, so it's slightly negative, carbon slightly positive. This molecule is polar, which means it can do dipole-dipole. And whoa, that's the answer. Both molecules can do dipole-dipole, so they can mix together. They have the same intermolecular force, therefore we predict they should dissolve in each other. Cool. Let's see. Milli equivalents per liter. Take a look at the video. I did a sample problem on how to get to equivalents. And we also have these examples, how to prepare solutions. There's a dilution here, I think. Yep, 6 molar. And you start with solid. So one of these to prepare from a solid compound, need the grams. The other one, you have to make a dilution. So take a look at the video. There's some sample problems in that. Okay, so we got concentration. Yeah, why don't we do this one? Oops, this is in my way. There we go. Okay, number 8. Suppose 2 milliliters, which is equivalent. It's the same as 1.58 grams of CH3OH, are dissolved in 35 grams of water, resulting in a solution volume of 37 milliliters. Okay, cool. This might be a little confusing, but we're just saying that there's 2 ways of getting the quantity of this. You can weigh it, and we can measure its volume, and we decided to do both. So depending on what you need, you got the info. All right, so what do we need to do? What's the concentration of this solution in molarity? So what you need to know is that molarity has mole in it. It's moles per liter. Okay, and then it's liters of solution, and it's moles of solute. What's missing? The solvent. So the solution is a solute thing being dissolved plus a solvent, the compound that we have the greatest amount of, and it's usually a liquid. Turns out this is a liquid, but you didn't need to know that. We got 35 grams of this and only 1.5 grams. Water's the solvent. So there we go. So moles of this thing, right? We said water's a solvent, so the other molecule must be the solute. What we want moles of the CH3OH. So let's do a little dimensional analysis and get it. Okay, so what do we know about CH3OH? We know the volume of it, and we know the grams. Is there something, a conversion factor that can take us to moles? Molar mass. So if we get the molar mass, that would be in units of grams per mole. So what you have to do is go to the periodic table and go look it up. So on our periodic table, it's 1.00. I know, it's silly I got these memorized, but I've done this so many times. It's just in there. So if you go to the periodic table, find the C's, find the H, find the O, that's element 8. And why is that 12? I guess I don't have this memorized. That's actually a 6. The atomic mass, though, I'm pretty sure it's 12. And let's round off, just to simplify everything. So oxygen's element 8, oxygen, and that's 15.9994 or something. Let's round off to 16, 12, and 1. So in one molecule CH3OH, there's one carbon that weighs about 12. There's 4 H's, each one weighs about 1. And there's an oxygen that weighs 16. 16 4 is 20, plus 12 is 32 grams per mole. Okay, so if I start with the grams, I can then cancel out with this. So let's get the grams to cancel. So do I multiply or divide by 32 grams per mole? I have to divide. Okay, I get the G on the bottom, so we can cancel it with this G on top, which means the 1 mole's up here. Oh, and I also have to get the moles on top because I need that as my unit. We're not dividing by moles over here, it's on top. So, yep, divide by the molar mass and things will work out fine. Calculator, what do you say? I know I'm using my silly phone. 1.58 divided by 32. I got 0.049 moles. So the molarity of the solution is 0.049. Hope that's right. It looks weird to me. And then we divide by the volume of the solution. Well, I got 2 milliliters. I got 37 milliliters. Ooh, but this one actually says solution volume. Good. Divide by 37 milliliters. Whoops, I need liters. So over here off the side, 37 milliliters. I need to change it to liters. So I need to cancel out the milliliters and swap in the liters. What's my conversion factor? It's 1,000. We'll have to remember that one. So divide by 1,000, and that'll slide the decimal place over 3. So there we go. So 0.049 divided by 0.037, and I get about 1.3 molar. That's the molarity. That actually was the hardest one. Weight percent. You just say, well, what's the weight of my solute? 1.58 grams. And then the bottom part is the total, the solution. Weight percent, the solute divided by the solution. And the solution's weight is not given. So you have to add the solute's weight to the solvent's weight. So 1.58 plus 35. And then we multiply that by 100 to get into a percentage, a weight percent. It's also the same as a mass percent. It's funny how the W's, if they're upside down, they're M's. Yeah, weird. Let's see, 1.58 plus 35 is 36.58. 36.58. 1.58 divided by 36.58 times 100. I got 4.3%. Hopefully that's right, but at least you see the process. And you do the same with the weight volume. The bottom number, keep using a solution, so it'll be 37 milliliters. Yeah, and then we got the volume of the solute, 2 mils up here. So those would be pretty straightforward. Number 9. Okay, so I'm looking at the clock and I don't have much time, I'm sorry, but let's set these up, or at least pick out the right equation. Yeah, so we got, we're supposed to calculate the heat gained or lost. So you're looking for Q. So go to the top of the equation of the exam or the sample test, and we got 3 equations that have a Q in it. So which equation do we need? Well, the first one has a delta T, which means the temperature is changing. That means if you have a solid and you change from one temperature to another, that's your equation. Or if you have a liquid and it stays a liquid as you change it from one temperature to another. Or you have a gas and they just change the temperature. There you go. This middle one, however, doesn't have a delta T. So that means you're doing a phase change. You're changing from one state to another. Which state? It's the state that involves a vap, which sounds like vapor, and a vapor is a gas. Yeah, so if you're going to a gas or from a gas, you use this equation. And if you cool a gas, what does it become? A liquid. There you go. So if you cool a gas to make it a liquid, you condense it. This is your equation for calculating how much heat it takes to cool a gas to a liquid. Or you can go the opposite way. You can take a liquid and change it to a gas. What's that process called? Boiling. Yeah. And when something boils, the temperature does not change. That's why there's no delta T in this equation. And then fusion's the other one we're missing. We want to fuse things together and make it solid. So this is where you're taking it from a liquid to a solid, you melt it. Or you take a liquid, did I say that right? No. Take a solid to a liquid, you melt it. Or if you take a liquid to a solid, you freeze it. So whether you freeze it or melt it, this is your equation. Cool. And that's what you need to know for number 9. Yes, number 9. So right here, for 88 grams of mercury is cooled from 322 to negative 20. Mercury remains a liquid, and you have a change in temperature. So you want that first equation, which was, you don't have to memorize, just go back and look it up. It's this one, delta T. So you got your change in temperature, which will be the final. So the final temperature is minus 20, minus the initial. Your specific heat, well, it's for mercury. You need to go look that up. And 488 is the number of grams. So specific heat of mercury, we need to go find that. And I'm going to lose all my writing, so that's okay. Go up here, and now you use the table. Here's mercury, and there's specific heat. So your conversion factor is 0.033. Use this number. Nice. Okay, I think you can get the rest of them. What else is important to go over? Oh, here, just the pattern. For number 10 and a bunch of the other ones that follow, identify what the property is, meaning a gas occupies 23 milliliters. So what property of the gas we're talking about that's measured as 23 milliliters? The volume. And what property is this thing? 322 degrees C, that's the temperature. Ooh, and a little red flag. If you're dealing with a gas, you have to switch to Kelvin. The gas laws, the equations don't work for gases unless you're in Kelvin. Okay, so we got a V and a T, and now it's saying what volume, and I always go, wait a minute, we know the volume is 23. Oh, wait, we're changing the temperature. So this is the first temperature, and here's the second one. And this must be the second temperature, and this is the first one. So now I need an equation with V1, T1, V2, V2, T2. V's and T's is what we need. So go to the top of the exam where all the equations are and find V's and T's. Here it is, right here. We divide. So it's V1 divided by T1 equals V2 divided by T2. Now remember, you must switch to Kelvin. It's the first equation right here. I can't highlight it, silly. Yes, I can. I'm gonna get it. There we go. So take the Celsius and add 273. Nice. Okay. That's 10. You can do the rest of those in a very similar fashion. Let's do 15 real quick. That's different. When the partial pressure oxygen gas, okay, partial pressure, that's talking about that part of the gas that's oxygen. You have a mixture. So take a deep breath of this mixture. Air contains nitrogen gas, too much air, nitrogen gas, oxygen gas, there's water vapor. Just put more water vapor in the air, fogged up my glasses. Carbon dioxide I exhaled. Sorry, carbon dioxide in the air. There's a bunch of other trace gases in here. But if we're only interested in the oxygen, then it turns out you can actually measure that. And so let's say we're at 1 atmosphere. That's probably what's happening here. And the amount of gas, that's oxygen gas, corresponds to 0.21 atmospheres, the partial pressure. So the partial pressure is like a capital P for pressure and a little subscript O2, meaning, hey, the partial pressure of oxygen is 0.21 atmospheres. And then what's 3 liters? That's a volume. And then what's 298? Ooh, Kelvin, thank you. It's already in Kelvin because we're dealing with the gas. Gotta keep it in Kelvin for gases. And it turns out the concentration of dissolved gas is 0.273 mm. Okay, the capital M means molar. 0.273 millimolar. Well, remember the M means moles per liter. So this number is millimoles of solute oxygen gas per liters of solution. And I know it might look a little weird, millimoles, but it's the same milli as in milliliter and milligram. Change it to moles, just like you change milliliters to liters. You divide by 1,000. Milligrams to grams, divide by 1,000. Okay. That's all interesting. I didn't see a question. Part A has a question. How many grams of oxygen gas are dissolved if the partial pressure of oxygen is reduced to 0.15 atmospheres? Okay, so that's an interesting question. They give us a new partial pressure and they want to know something about how much dissolved when we already had it. So a new quantity of dissolved. Let's go back up to here and think about this one more time. We got this partial pressure of oxygen. It's just in the air, about put it in a box. And then we have this maybe a beaker of water. And in here is 0.273 millimoles per liter of dissolved oxygen. So the more oxygen gas that's above it, the more pressure it is, the more that the pressure can push the oxygen gas into the water. That was Henry's law. So that's the relationship we want to realize, is that this whole question is talking about gas over a liquid, and the higher the pressure of the gas, the more of the gas will dissolve. And of course, if you reduce the pressure, more of the gas will bubble out of the solution and less will be dissolved. So we need something that talks about pressure, P, and concentration, either a capital M for molarity or maybe a C for concentration. We need a P and a C. And I didn't clean up my screen, so it's still gonna be messy. So go up here and it's right there. There's a C and a KP. Here's Henry's law. Concentration equals some K, some conversion factor times the pressure. Can I line things back up again? Maybe. There we go. Alrighty, so C equals KP. So here's the idea. Go back to the that's not the question, the statement number 15. Question number 15 says, hey, the pressure P is 0.21 atmospheres times K equals C, which is 0.273 millimolar. So divide both sides by 0.21 atmospheres, and the K is going to equal 0.273 divided by 0.21, 1.3. And the units, well, the millimoles are over here, and I divided by atmospheres. So that's my K. Why do I want that? Because question A says Well, it said grams, so it's going to complicate it. But let's just go after Henry's law. We want to know if the partial pressure is reduced to 0.15. So now we have a P. The P is now 0.15 atms. And K is a constant. And constants, by definition, don't change. So the constant here is 1.3 millimolar per atmosphere. And that equals C. So you multiply these two together, 1.3 times 0.15, the C is equal to 0.195. The atmospheres cancel, and we're left with millimolar. Millimoles per liter of oxygen gas is dissolved. But dang it, they want grams. So dimensional analysis. What do I want? Grams. And let's see if I can squeeze in here. What do I know? This number. Oh, wait. We're supposed to start with a single unit, right? When we do dimensional analysis and we're picking a number, we want to start with a single unit number. And the capital M is 2 units. It's millimoles divided by liters. So I don't want to start with that. What else do I know? Well, what else am I given here? I want to get them, there's moles here, but I don't see moles anywhere in the question. But there's liters here. Liters per solution. That's what this M stands for. And I actually do have liters of solution right here. That's what we want to start with. So 3.0 liters of solution. And then we're going to multiply by this. Yeah, we're going to multiply by this number, which is 0.195 millimoles of oxygen in 1 liter of solution. And this is 3 liters of solution. Liters of solution cancel out. And now we have to get out of millimoles. So we said there's 1,000 milli anythings in a thing. 1,000 milliliters in a liter. So there's 1,000 millimoles in 1 mole. So 1,000 millimoles in a mole. So the millimoles cancel out. And then we want grams. So cancel out the moles and go to grams with the molar mass. Go to the periodic table, find out the weight of oxygen. It's about 16. Multiply it times 2, that's 32. So oxygen gas weighs about 32 grams for every 1 mole. And then multiply across your top. So my calculator already says 0.195. So multiply it times 3. Multiply it times 32. So across the top, I got 18.72. And across the bottom, I multiply 1 times 1,000 times 1. So the denominators all multiply out to 1,000. So I divide these two. And the number of grams, that's what I want, is 0.0. How many sig figs should I get? I think I got 3.0. There's only 2 sig figs, so let's just carry 2. Looks like 19 grams of oxygen gas. Yay, nice. Okay. So I think that's all for now. Good luck on the exam. Send me an email or actually post a question in the discussion board if you have questions, and I can help you out there too. All right, good luck on the exam.